Hey crazies, I've said several times that light doesn't have mass, and this has confused quite a few of you. For most of you, the issue seems to be, doesn't everything have mass? Why wouldn't light have it too? Or sometimes, light has momentum, doesn't that require mass? All of which are fair questions. But I think it'll be best to start with Ashley Hughes, who gave this question some useful context. Most of the light arriving on Earth from space,
outer space,
comes from the sun. You know, that big glowy ball at the center of the solar system? In the core of the sun, nuclear fusion is smashing protons together. More details on fusion in an upcoming video. Every 4 protons comes together to make 1 helium nucleus. But 4 protons have more mass than 1 helium nucleus. About 50 electrons worth of mass, which is enough to worry about. Since lots of fusion reactions are happening inside the sun all the time, the sun is losing mass at a rate of about 4.3 billion kilograms per second. That's 3 million jettas per second. Which might leave you wondering, where did all that mass go? It was released as light. No, seriously, light is like the exhaust of the sun, yet it powers our entire ecosystem. How cool is that? But how can mass be lost as light if light doesn't have mass? E equals mc squared. It's energy. No, haven't you said this? Energy doesn't disappear or start floating around on its own. It goes into other atoms, molecules, or particles. Right, that energy is contained by the photons of light. But didn't you also say this? There is no difference between mass and energy. Oh crap, that is a problem. If mass and energy are equivalent, then anything with energy should have mass. Light has energy, so it should also have mass. Wait, hold on a second. We have to be really careful about the word mass. We don't want to get it all muddled up with our preconceived notions. Let's start with how we perceive mass. Because of general relativity, we know light is affected by gravity, which certainly makes it look like it has mass. Light can also create gravity. If you have enough of it, you can even create a black hole. It's called a Kugelblitz. Where relativity basically throws mass out the window. Gravity is the result of curved space-time. And space-time is curved by energy, momentum, pressure, and/or stress, not just by mass. Honestly, because of E equals mc squared, you could just as easily call it mass. Okay, we also know the more massive something is, the less willing it is to change how it's moving. That's what we call inertia, which we covered in this video. Light doesn't ever change its motion. It always travels in straight lines at a very fast but steady speed. Fast! So it has infinite inertia and therefore infinite mass? Wait, that can't be right. Hold on. We know light has energy because it has to carry something away from the nuclear reaction inside the sun.
Conservation of energy shall not be violated.
Now, momentum is more closely related to inertia than energy is. But we know light has that too because it can do this. The light collides with the blades and gives up momentum, which makes the blades spin. So light must have momentum. And since it can't have an infinite amount of momentum, it can't have an infinite amount of inertia either. Whew, crisis averted. But it has some inertia though? Well, yes and no. When you think of your own mass, you think of all the stuff that makes up your body. It's something you have even when you're sitting still. But light doesn't ever sit still. Ever. It's physically impossible for light not to go at the speed of light. So you can't just equate the two concepts. But E equals mc squared? Okay, we'll take a closer look at it. It's probably the most famous equation of all time, except it's kind of a lie. It actually looks like this, where the letter P stands for momentum, from an old Latin word meaning to go. If the thing isn't moving, the equation reduces to E equals mc squared. If instead there's no mass, the equation reduces to E equals pc, which applies perfectly to light. So light has no mass. Some people want E to equal mc squared so bad, they do this, where this m is a rest mass, and this m is called relativistic mass. But that's kind of silly. It's much easier just to forget about mass altogether and use energy and momentum instead. Theoretical physicists did it a long time ago. So let me know in the comments, are you satisfied with this answer? Or would you rather distinguish between rest mass and relativistic mass? Thanks for liking and sharing this video. Don't forget to subscribe if you'd like to keep up with us. And until next time, remember, it's okay to be a little crazy. In the last video, we learned why planets orbit in a plane. Comment response time. Jesse LaJeunesse asked if galaxies were just really big accretion disks. Yep, they are. I can understand how you might think the physics shouldn't scale up like that, but if it makes you feel any better, that's as far up as it scales. You'll notice galaxy clusters aren't disks. The shape of the large-scale universe depends on how it originally formed, much more than on conservation of momentum. Nunya Business was wondering why the plane of the solar system was roughly perpendicular to the sun's magnetic field. As it turns out, the rotation of the sun is roughly parallel to the plane of the planets, which shouldn't be much of a surprise since it was all rotating together to begin with. But the sun's magnetic field is generated by convection currents in its middle layers. How those currents behave depends on the direction the sun is spinning. So the magnetic field of the sun tends to be perpendicular to its rotation, something that's actually true of planets as well. Amy Soderstrom and Megan Gilmore were wondering where the gravity comes from that collapses the gas cloud in the first place. Anything with lots of mass will create gravity, including a very thin gas cloud. It might not have been very dense, but it was big, like light years across big. It contained all of the mass that will form the sun, the planets, and all the comets and asteroids. That's a lot of mass no matter how dense it is. So the cloud itself creates the gravity that collapses it. To answer K8UR's questions, yes, all planetary systems are disks, but they're not all parallel. We've seen a lot of them with telescopes, which just confirms our hypothesis on how they form, but we see them from a bunch of different angles. A lot of them have stars at their center, but others have multiple stars orbiting a common center. It depends on the complex details. Okay, crazies, the next video is the 100th video. It might not go up until early November though. There's a lot going on with me right now. There are more details about that in my most recent vlog. Click anywhere on my face or the mobile card somewhere up there. Yeah, in case you didn't know, I have a vlog. Anyway, thanks for watching. I'll see you for the 100th. You can model light as having mass and materials because it seems to travel slower in them. Ugh, but you can also model a bubble as having negative mass because it goes up instead of down. Yeah, wrap your head around that.